This is part one. Part one is the circular motion stuff. There are 4 problems on here, and they match up pretty well with the 4 problems that are on the test. So there's one that's just a straight up gravitational law formula where you use Newton's law of gravitation. There's one that's about a something in a vertical circle. On the test, this was somebody at the bottom of a circle driving a car in this part of a loop. It could be the top of a circle on the retake. It could be the bottom again. This one is about something orbiting something else out in space, and that's going to be a 2-part one. And then there's another one about finding G, or using the formula to find G to find something else. So the first one, there's really not much to say here. You're given a mass, you're given another mass, you're asked to find the force of gravity between them. So you just plug in those masses, multiply them together, and then divide them by the square of the distance between them. And then multiply that by the gravitational constant, which is right there. So if you're having trouble with the computation of this, come and see me or talk to somebody else. I'm not going to go through all the calculator work in this video. But if you set everything up like this, you will have almost all the points. No matter how bad this is, this was a 4-point question, and you'd only lose a half a point if you had some number of newtons here and you had all this written out correctly. And if you had 1.92 times the wrong power of 10, that should say 10 to the 7th, not times -7, then it's only a quarter of a point. Number 2, on the test, this was about somebody at the bottom of a circular swoop. Here, this is about somebody at the top. So I might ask you about the bottom or the top. And this one I should explain a little bit more about. So let me I guess I'll tell you what I did here, and then I'll talk about what you would do if this were at the bottom. But you could watch the test video for that. So since this is somebody at the top and they're in circular motion, then we know that the net force is equal to mv squared over r. That is the net force when something is in circular motion, uniform circular motion. And the reason this is negative is because at the top they're accelerating toward the center. In circular motion, you're always accelerating in the direction of the center, which means when you're at the top, you're accelerating down because the center is below you. But then if you're at the bottom, you're accelerating upward because the center is above you. So if this problem were taking place down here at the bottom of it, we would say the net force is positive mv squared over r. I won't complicate things by asking you what's going on over here. If you're over here, then the net force would be to the left. But we're not bothering with that kind of a situation. So that's the net force. The way you solve a force problem is you write F equals ma. This is basically F equals ma, because in a circular situation, A is v squared over r. The second step in one of these force problems is to add up all the individual forces and write net force that way. So that's what I'm doing here. There are 2 forces acting on the person. There's the weight of the person pulling them down, and then there's this surface up here, or whatever they're sitting on, that's pushing them down. That's the normal force. And that's it. There's no drag in here unless I specify, and I won't because I'm not going to have you calculate drag. So this is the net force, and this is the net force. And it's important that you make sure all your signs are correct. It's negative mv squared over r because the center is below you and we're accelerating toward the center, so the net force is toward the center. And this normal force is negative because the surface pushes down. If you were sitting down here, then the surface would be pushing you up and the normal force would be positive. mg, the weight, is always downward, whether you're at the top or the bottom. But at the top, both the normal force and weight are negative. So here's the net force expressed one way, here's the net force expressed the other way. Now I just set them equal. I take this and put it here, take this, put it there, and that's my basic equation. Now I'm given some other information. I'm told that the weight is 600 newtons, so I can just plug that in for mg. And here it says, even though they're upside down at the top of the loop, they feel heavier than normal, as if they weigh 900 newtons. So on the test, I won't be tricky like this, but your perception of weight is your normal force. So if this person had a normal force of 600, they would feel their normal weight. They're feeling a little heavier than usual. But however heavy you feel, the perception of weight, that is the normal force. So that 900 newtons, I can just plug in right here. And so this becomes negative, or this is 900 and this is 600. And it looks like I took this whole thing and I multiplied both sides by -1, because you see all the negatives disappear. So this is positive 900, this is positive 600. And then I've plugged in mv squared and everything except r, which is what I'm solving for. M is not given, but if you have weight, you can find mass. Weight equals mass times 9.8. M times 9.8 is 600. That's the weight. This is G. This is M. So M has to be 61.2. So plug all that stuff in and then solve for R. And I didn't show my algebraic steps, but I would be multiplying both sides by R and then dividing both sides by 1500. So just add these together, get 1500. So basically 61.2 times 20 squared divided by 1500 equals R, and R is 16.3. If this were at the bottom, then and all this other stuff were true, then we would put in it would be positive mv squared over R. That'd be the net force here, and positive 900 right there, because that's the normal force they feel, minus 600, the weight, and you would get a different R in that case. So be ready for a problem either with somebody at the top or the bottom. Number 3, this is the one where something's orbiting something else, and I'm just going to draw a new picture out here. If you have a thing, I'll make the mass of the little thing a little, kind of a little curvy m, orbiting a big thing. I'll make the mass of this a big pointy m. The thing that keeps objects in orbit is the force of gravity. And out in space, there's only the force of gravity. So if I want to write the equation for net force, it's just the force of gravity. But since this is circular motion, the net force is also mv squared over r, where this is the mass of the thing going around. And r would be this distance right here, distance from the orbit to the center of the thing being orbited. So force of gravity, I can use Newton's law of gravitation to get an expression for that, which would be big G times the two masses multiplied by one another, so the big mass times the little mass over r squared. And so this is the force of gravity, which is the net force. This is centripetal force, which is the net force. So I just set these two equal. mv squared over r equals g times big M times m over r squared. And this can be simplified because there's a little m, there's this mass on both sides, and there's an r and an r squared, so I can multiply both sides by r. And when I do that, these cancel out. That squared goes away. So I get v squared equals g times the mass of the planet over r. And that's a useful equation. I don't know if I'm going to use that first or if I'm going to use it second. So in this case, I can use it first. Let's see. Because the elephant, that's the thing that is being orbited. So I'm given its mass, so I can plug in 10,000 kilograms right there. And I'm given the orbital radius, that's 6, and g you're given at the beginning of the test, so you can solve for v. V comes out to 3.3 times 10 to the negative 4th meters per second. I think on the test, you had to do this kind of thing first. So you're either going to have to do this kind of thing first and then this, or you'll have to do this and then this. Doesn't really matter as long as you can set up an equation like this. If you don't have everything you need in order to solve it, then you just move on to the other step, which is to recognize that something that's going around like this in I'm going to say delta t equals big T. Big T is just the symbol we use for period, which is the time it takes for something to rotate. And distance equals rate times time. Rate is velocity, and time in this case to orbit is big T, and the distance that something has to go in order to orbit once is the circumference, which is 2 pi r. So you can have another equation here, 2 pi r equals v times t. And like I was telling you, in some cases, you're going to have to plug stuff into this in the first part of the problem and find maybe v, and then put v into here, and then maybe find m or r. But in this case, you find v first, and then you can take that v, plug it in there, and what we're trying to find is t. So you know r, 6 meters. So you can solve for v. So let me just go back to this. I'll talk through the specifics of what was here. So the net force is mv squared over r, because it's going in a circle. Net force is gravity. Set these equal, come up with this equation, and plug in that for g, this for the mass of the thing being orbited, the elephant, this for r, and that's v. And then I've got my other equation, time, or period, equals distance over velocity, and the distance is 2 pi r, 2 times pi times 6, over v, which I just found. So it's this many seconds. The third type of problem, or sorry, fourth type of problem. So we've got one problem that's just straight up law of gravitation. One problem that's a vertical circle, either top or bottom. One problem, something orbiting something else out in space. And then a fourth problem relating to finding g, little g, not big G. And I changed this. The solution is right now, but the problem is different. So this was about the Concorde and how high it flew, and on and on and on. If you know this is the one that involves little g, then you don't, I'm not even going to read all the details. I'm just going to tell you this is what I do. This is how you're going to solve this thing. Weight is the force of gravity, and we used to only have one way to calculate weight, and that was mg. But the other way we can calculate weight now is with g, mm over r squared. So my weight is gravitational constant times the mass of the Earth times my mass over the distance between my center and the Earth's center squared. That's the force of gravity, which is what weight is. So we can set these two things equal. This is my mass times g. This is the Earth's mass times my mass. There's my mass on both sides, so I get this formula. G, little g, the acceleration of gravity, which is normally 9.8 meters per second squared, equals gravitational constant times the mass of the Earth, or the thing being orbited, or the thing that's causing the gravity, divided by the distance between the object experiencing the gravity and the center of the planet. So in this particular case, with the Concorde, I just use that formula. G equals big G times the mass of the Earth over r squared. And r is the, is this 6.39 times 10 to the 6th. That's the distance of the passengers from the center of the Earth. So it turns out they're experiencing a value of g equal to 9.75 meters per second squared. Be ready to solve for something else. The variables that you may need to solve for are little g, or r, or the mass of the planet.